Ha ha ha! It is video time. 2019 questions 5 and 6 in this video. So, hope we're doing well today. We're about to finish up all the AP exam questions from 2014 to 2019. That's crazy. And we will figure out what to do after this point later on. All right. Start with question 5. It says consider family function f of x equals 1 over x squared minus 2x plus k, where k is just some number constant. And it says in part A, find the value of k for k greater than 0 such that the slope of the line tangent to the graph, so we know that means f prime, such that f prime of the graph of f at x equals 0 is 6. So this is saying find k where f prime of 0 equals 6. Okay, so we need to start with finding what f prime of x is. So f prime of x equals. All right, and I chose to do this as I chose to do x squared minus 2x plus k. I raised it to the negative first power and did it that way. So the derivative would be negative and then x squared minus 2x plus k to the negative second now, and then times the derivative of the inside, which is 2x minus 2. Okay. Which if I want to rewrite that in a nice simplified form, I could say this is negative 2x minus 2 on the top, and on the bottom I got x squared minus 2x plus k quantity squared. Okay. So that's f prime of x. So then f prime of 0 is going to be 0 plugged into that. So that's going to be on top, that's going to be negative 2 times negative, which is positive 2 on top. And on bottom, it looks like I just got k squared when I plug 0 in. I'm trying to solve for k when this equals 6. Okay. Just doing a little bit of math here. That's 6k squared equals 2. K squared equals 1/3. And because k is greater than 0, I'm going to take the square root. I don't need the minus part, so k is just going to equal the square root of 1/3. There you go. That's part A. Not too terrible. All right, B says, now k is negative 8, and I want to find the integral 0 to 1 of that. All right, well, let's see what that looks like. So this is saying I want to find the integration 0 to 1 of 1 over x squared minus 2x minus 8. And all I have to do is just figure that out. All right, here's the thing. So how do I integrate that? Okay, this is actually going back to our integration, our techniques of integration from the BC, the first unit here. You could try U sub, it doesn't work. You can try all sorts of stuff, but actually we can do partial fraction decomposition. So think of it this way. We could say, all right, this is the same thing as x minus 4x plus 2. So I can split this up into two fractions and then integrate each of the pieces. I think that's the easiest way. All right, so we can say like that 1 over x squared minus 2. I'm going to actually write it this way. 1 over x minus 4 times x plus 2 is equal to a over x minus 4 plus b over x plus 2. Right? And then, multiplying by the LCD, we end up getting 1 equals a times x plus 2, because the x minus 4's cancel, and b times x minus 4. Oh, come on. Dude, why does it do that? I don't know. There's a 4 right there. Just do that, I guess. Not squared. Boom. Okay. All right, so we're gonna let's start off by maybe I'm gonna let x equal negative 2. So then the a cancels and I get 1 equals b times negative 6, or b equals negative a sixth. Let's let x also equal 4. The b cancels, and I get 1 equals a times 6, or a equals a sixth. Okay, so there's our partial fraction decomposition. So what I'm left with is really the integral 0 to 1 of, now a is 1/6, so I'm going to say 1/6 and then x minus 4. So that's the first one. And b is negative 1/6, so I'm actually going to say minus 1/6 and then x plus 2. Right? There you go. That is our, well, that's what it breaks down to. And we can integrate each of these pieces, right? I know what each of these integrates to. 1/6 x minus 4 on bottom there, that's just going to be ln, or 1/6 I should say, 1/6 absolute value x minus 4, and then minus 1/6 ln absolute value x plus 2. Okay, so that's the integration, and we're evaluating this from 0 to 1. So we'll plug in 1, we'll plug in 0, and see what we get. Okay. And for sake of space, I'm going to go ahead and combine these together to be 1 ln by the minus sign. Remember, we can divide the quantities. So I'm actually going to say this is 1/6 ln absolute value of, and then x minus 4 divided by x plus 2. So I'm going to say 1 minus 4, which is negative 3, over 1 plus 2, which is positive 3. So that's when I plug 1 in. And then minus 1/6 ln of absolute value. If I plug 0 into that, that's negative 4, and then divided by 0 plus 2 is 2. Okay. And this becomes, now this left quantity here becomes the ln of absolute value of negative 1, or the ln of 1. And the ln of 1 is 0, so that goes away. So I'm left with my final answer to be negative 1/6 ln, and absolute value of negative 4/2 is just 2. And that's my final answer, negative 1/6 times ln of 2. And then part C here says for when k is equal to 1, all right, find the value of the integration from 0 to 2 of f of x, kind of like we did in B, or show that it diverges. So what's asking us to do here is look at it this way. So this is the integral 0 to 1, or I'm sorry, 0 to 2, of 1 over x squared minus 2x plus 1. Okay. Now, this looks like a very similar integration to B, so let's think about how it factors. It's actually going to be x minus 1, x minus 1. So what I'm left with is the integral 0 to 2 of 1 over x minus 1 squared dx. Okay. Now, we can integrate that, but here's the issue that they were wanting you to recognize here. Okay, we can integrate that all day, but if you notice that there is an undefined value for x within our integral, 1 does not work. So what we have to consider is this as an improper integral. Okay, that's what it's testing you here. Is what a lot of students probably did is they just integrated it, plugged in 2, plugged in 0, and they were done. But they have to consider the fact that 1 is not defined in the interval. It's an absolute. It's a. That's what I'm looking for. It's a vertical asymptote. Okay. What this function looks like, if you're at a graph, I know you don't got a graphing calculator, but it's shifted to the right 1, so it's right here, and the squared makes it look like this. Okay. So we have to treat it like an improper integral. Okay. All right. So how it's going to work. So remember that the undefined point is at 1, so we got to break it up this way. We got to say that was the integral 0 to 1 of 1 over x minus 1 squared dx plus the integral 1 to 2 of 1 over x minus 1 squared dx. Okay. So we got to break it up at the point that it was undefined at. And then we have to turn this into a limit. All right, we have to say, okay, well, we're going 0 to 1. We're going to 0 from the left on this side. So I'm going to say the limit as r is approaching 1 from the left of integral 0 to r, right, of 1 over x minus 1 quantity squared. Okay. And this is going to be plus the limit as r is approaching 1 now from the right. We're coming from the other side. And we're going to say r to 2 of 1 over x minus 1 squared dx. There you go. Okay. Now we just integrate and plug in 0 and r and 2, and we take the limit. See, and remember, if it's all quantities, all numbers, then it is going to converge to a value. If there's any undefined or infinity in there, it's going to be divergent. Okay? All right, so let's see here. Let's do this piece here. This is going to be the limit. R is approaching 1 from the left. All right, now if I integrate 1 over x minus 1 quantity squared, that's going to end up being, I think it's just negative 1 over x minus 1. Yeah, and we're evaluating that from 0 to r. And then plus, I'm about to sneeze, the limit, bless me, as r is approaching 1 from the right, and then it's the same integral, negative 1 over x minus 1, and we're going from r to 2. Okay. All right, now if I write that out, so do the first one here. It's the limit as r is approaching 1 from the left of, if I plug in r into that, that's going to be negative 1 over r minus 1. And then minus, if I plug 0 to that, that's going to be negative 1 over negative 1, which is just 1. And then plus the limit as r is approaching 1 from the right. If I plug 2 into that, that's going to be negative 1 over 2 minus 1. So negative 1 over 1 is negative 1. And if I plug r into that, it's going to be minus negative 1 over r minus 1. Okay. Now let's take the limit. Okay, we're going to take the limit of each of these pieces. If I go to 1 from the left of negative 1 over r minus 1, okay, you can, this graph right here, if you want to think about what that graph looks like, negative 1 over r minus 1, it's just 1 over r that's shifted to the right one and flipped, so it looks kind of like, let's see here, it looks like this, I believe. So as we approach 1 from the left, we're going to infinity, so this is infinity minus 1. And then plus negative 1 minus, and if I go to 1 from the right, we're going to negative infinity. So there you go. Now, because we have the quantity infinity in here, it's just got to be in there once, we can say therefore, that's the therefore symbol, therefore the integral 0 to 2 of f of x diverges. There is no value. Okay. So that was number 5. All right, here's the points for it. You can see for A, we got the correct denominator for f prime. So we got the right f prime of x. And I guess 2 points for that, really. And then 1 point for the answer of being square root of 1/3. B, we get the correct partial fraction decomposition, which was, they wrote it this way, but I always write the 1/6 kind of combined. I already simplify it. The correct antiderivatives, which is what we got, and then the answer to be that. And honestly, if you left it here, you would have been fine. And then C, we get 1 point for the improper integral, so the fact that we knew to set it up as an improper integral. The correct antiderivatives, okay, and then the answer with a reason that, hey, it's divergent, and it's because, well, they just talked about the first piece of it, but yeah, both pieces of it are actually divergent. Okay, so there you go. Cool. Now let's move on to number 6. Number 6, I would say, as far as we are concerned, know how to do A, know how to do B. C and D, maybe C, but D definitely not. D definitely not. So let's start with A. This is a function f has derivatives of all order for all real numbers x, and a portion of the graph of f is shown above. All right, so f looks like some weird function. It almost looks quadratic, but it has a weird little curve. But anyway, here's f. And it says along with a line tangent to the graph of f at x equals 0, and selected derivatives of f at x equals 0 are given in the table above. So it looks like we're centered about 0, right? And it says write the third degree Taylor polynomial for f about x equals 0. So you need to know how to write a Taylor polynomial. And in this case, since we're centered about x equals 0, that is a Maclaurin polynomial. Okay, so let's write out the formula so we can memorize it. Remember that a third degree, okay, so that's p3 of x. Remember how Taylor polynomial works. It's going to be f of 0 plus f prime of 0 times x over 1 factorial, which is just 1, plus f double prime of 0 x squared over 2 factorial, and then plus f triple prime of 0 x cubed over 3 factorial. Okay, so as long as you know the formula, then it's just all about trying to find this value, this value, this value, and this value, and then we're good. All right, well, let's find them all. So f of 0, the graph of f is given, and here is f of 0 right here on the graph. F of 0 is just 3. F prime of 0 is just the slope there, and it gives us the tangent line. And if you do a little rise over run there, that derivative is down 2 over 1. That's a slope of -2. So the graph gave you f of 0 and f prime of 0. F double prime of 0 is given in the chart here. All right, so this is saying the second derivative is equal to 3. And the third derivative is also given in the chart, and it is -23 over 2. So then P3 of x, my third degree Taylor polynomial, is going to be f of 0, 3, plus, I guess I should say minus, because it's -2, minus 2x, and then plus 3 over 2 factorial, or 3/2 x squared. And then it's going to be plus, but minus because it's negative. So minus 23, 23 over 2 divided by 3 factorial times x cubed. And honestly, you can leave it that way. It's a third degree Taylor polynomial. We won't require to simplify it. But to help us out a little bit later, 23/2 divided by 3 factorial. If you simplify that out, that's 23/2 divided by 6, which is going to be 23 over 12. So I would probably simplify it because we are going to have to use this later, and I think that's good. So know how to make a Taylor polynomial from the definition. I think that's pretty helpful. Okay. All right, then B says write the first 3 non-zero terms of the Maclaurin series for e to the x. Give me point right there. Just knowing the Maclaurin series for e to the x. I'll write that up here. Remember that e to the x, okay, in Taylor series form is the summation n equals 0 to infinity of x to the n over n factorial. That's something you need to memorize, which the first 3 terms of that is going to be 1 plus x squared over 2. Okay, those are the first 3 terms simplified out when you plug in 0, 1, and 2. Okay, so there's your first give me point. And then it says write the second degree Taylor polynomial, so only to the power of 2, for e to the x times f of x. Well, I got the Taylor polynomial for f of x from A, and I got the Taylor polynomial for e to the x just given to me here, or from knowledge. So if I want to know the Taylor polynomials for the product of the two, you just got to multiply them, right? So e to the x was 1 plus x squared over 2. And f of x that we got from part A was, I mean, it goes on infinitely, but we did it to the third degree, which was 3 minus 2x plus 3/2 x squared minus 23 over 12 x cubed. Now, technically, both of these series goes on to infinity, right? But we're only going to the second degree, so I only need to take the product of those two Maclaurin series up to the second degree. So we're going to keep multiplying and distributing until we're past the second degree. So like for instance, I'm going to do 1 times 3 times negative 2x times 3 halves x squared. I'm not going to multiply it by this cubic term because that's past the second degree. So what I have so far is 3 minus 2x plus 3 halves x squared. I'm going to multiply everything by x, that by x, that by x. I'm not going to multiply x by 3 halves x squared because that's going to become a cube value. So this is going to be plus 3x minus 2x squared. And then lastly, I'm going to do x squared halves times 3, but not times the negative 2x because that's a cubic term. And that's going to be plus x squared, well, I guess plus 3 halves x squared. And there you go. So it wants the first 3 non-zero terms in the Maclaurin. Okay, so write the second degree Taylor polynomial. So I guess we'll call that, I'm not even going to label it anything. We're just going to find the second degree Taylor polynomial for this. And so we need to simplify it down. So I'll start with the constants, which is just, I think, 3. Yeah. Then the linear terms is negative 2x and positive 3x, which is just plus x. And then my square terms are these 3 values together, which is 3 halves, and negative 2. 3 halves and 3 halves is 6 halves or 4. 4 and negative 2 is just positive 2x squared. Making sure I said that correctly. Or wait, no. 3 halves and 3 halves is 6 halves. 6 halves is 3. 3 minus 2 is just positive 1x squared. So that's what it simplifies to. And there you go. I mean, that is the second degree Taylor polynomial for e to the x times f of x. We had to stop at the power of 2. Okay. All right. So A and B, I would hope that you can get. That's kind of where I want you to be at right now. And C and D, C maybe. I think C is doable. But D is part of an error bound, which we're not doing anymore. Okay. But anyway, C says, let h be the function defined by h of x equals the integral 0 to x of f of t dt. Okay, so we got f from part A, pretty much. It says use the Taylor polynomial. Yeah, use the Taylor polynomial found in part A to find an approximation for h of 1. Okay. So h of 1 is approximately going to equal the integral 0 to 1, because I plugged 1 in for x, of f of t. And if I'm using f of t from part A, we know what that is. That was 3 minus 2x, or I guess 2t, plus 3 halves t squared minus 23 over 12d cubed. So we're approximating h of 1 by using, h of x equals this, and I'm approximating that because I don't want to put the infinite f of t. I'm just doing up to the third degree like I did in part A. Right? So that's it. We just integrate and solve. So I'm going to do it up here. Integrating that is going to be 3t minus t squared plus, I think that's 3 over 2 times 3, so is that 1/2 t cubed if I integrate that, right? Yeah. And then minus, that's 23 over 12 times 4, or 23 over 48 t to the 4th, and we're evaluating this from 0 to 1. Well, if you notice, if I plug 0 into that, it's going to cancel everything out, but if I plug 1 into it, it's going to be 3 minus 1 plus 1/2 minus 23 over 48. And guys, if I were you, I would leave it in that form right there. Don't try to simplify it, but just in case you did, it does simplify to 97 over 48. Okay. So there's our approximation. We approximated h of 1 by using the third degree Taylor polynomial from A and A. So it's approximately equal to 97 over 48. Okay. And then lastly, D, doing an error bound here. Okay, so it says, this is a kind of a weird one. It says, it is known that the Maclaurin series for H converges to H of X for all real numbers X, and it also knows that the individual terms of the series alternate in sign and decrease in absolute value to 0. All right, you may not recognize it, but what it just said decreases to 0, alternates in sign, and it converges. So it gave me the requirements for the alternating series. Basically, it's saying that this series is convergent by alternating series test, and if that's the case, then it follows the error bound for alternating series. So it says use the alternating series error bound to show that the approximation found in part C differs from h of 1 by at most 0.5 or 0.45. Okay, so this is just a fancy way of doing alternating series bound. Okay, so this is what I want you to think about. Remember that alternating series bound says that we're going to take the actual sum minus the partial sum, and that's going to be less than or equal to the next term in the series, the next term that we haven't used, the first term we haven't used, I guess. Okay. So S in this case is the actual value of h of 1. S of in here, that was what we approximated in part C. That was, I guess we'll call that P3 of 1, using that Taylor's polynomial of third degree. And we got to think about, all right, what is the next term's value? That's what we got to figure out. Okay, well, remember what we did here. We're doing this for h of x, okay, which what we did, we used the integrals of the answer in A. So those terms were 3t minus t squared, 3t minus t squared, plus 1/2, oops, that's ugly, minus 1/2 t cubed, and then minus 23 over 48 t to the fourth. So the next term in the list is the one that we need to use for our value here, okay? Which, how do I get this next term in the list? Well, remember how we got these other terms is we integrated from 0 to 1 the terms from part A, which I got this by integrating the third degree. I need to get this by integrating the fourth degree, which comes from this value here. The fourth degree one was, it'll be 54 over 4 factorial times x to the fourth. So I need to integrate 54 over 4 factorial is 24. And actually, 54 over 24, what does 54 over 24 reduce down to? 9 over 4? Yeah. So really what I'm integrating here is the next term in the list, which is going to be 9/4 t to the fourth dt. Which, if I integrate that, it's going to be 9 over 20 t to the fifth from 0 to 1, which is just going to be 9/20. So this is the next value in the list. All right, that's the next value in the list if I were to keep going, right? So basically what I'm saying is that the error, all right, the error is going to be less than or equal to the next term's value, which is 9/20, which actually equals 0.45. So there you have it. I mean, we just showed by finding the next term. The only thing that sucked about this one was figuring out what the next term was. Okay, I mean, the next term was found. I mean, it was the next term in h of x, which was found by integrating the terms from f. Right? And we got that equaled 9/20, which is 0.45. So the error is not going to be past that. Alternating series error bound can be kind of annoying, so it is a good thing it's probably not on your AP exam. All right. Here's the answer key. So we got the two terms here for the first two terms and the remaining terms. It only gave you 2 points really. Then we got the first two terms and the last two terms, which we simplified down to this in part A. Part B is that we got the first three terms for e to the x. That's just a formula that you memorized. And then we get the remaining point for multiplying that by the answer from A and simplifying it to 3 plus x squared. C, we get a point for the correct antiderivative, so getting to here, and then 1 point for the answer, so there. And then D is a point for using the fourth degree term of the Maclaurin series of f, okay? So using that value and then integrating that, all right, integrating that to get 9/20ths, and then that gives us our error bound. So there you go. So that's 2019, yay! And yeah, so we'll talk about kind of where to move forward from here later, and just get all these years submitted to me, and we will be set. Good job, guys.